Let's consider various species of carbon, oxygen, and nitrogen molecules, starting with the most common neutral arrangement. Here we have a molecule containing carbon. Carbon always has 4 valence electrons. There are 4 electrons associated with this carbon, half the number of bonded electrons, so 8 divided by 2 equals 4, and all the lone pair electrons. There are none here, so 0. The number of valence electrons minus the number of electrons associated with carbon equals the charge. Thus 4 minus 4 equals 0, so neutral. All in all, there is a total of 8 electrons, 4 electrons associated with carbon and 4 shared with R through covalent bonds. We have a complete octet. The shape this molecule adopts is tetrahedral. When considering all these species, we will here focus this issue of shape particularly upon carbon, the atom of most interest to organic chemists. With oxygen, there are always 6 valence electrons. 6 electrons are associated with this oxygen, from 4 divided by 2 equals 2 in covalent bonds, and 4 in lone pairs. 6 minus 6 equals 0, so again, a neutral charge. Ultimately, there are a total of 8 electrons, 6 associated with oxygen, and 2 electrons from R shared via covalent bonds. A bent shape is observed in this case. How about nitrogen? Well, here it is. Nitrogen always has 5 valence electrons. In this situation, there are 5 electrons associated with this nitrogen atom, due to 6 divided by 2 equals 3 electrons from covalent bonding to R, and 2 in lone pairs. 5 minus 5 equals a charge of 0, so neutral. The total number of electrons in nitrogen's outer shell is 8, with 5 associated with nitrogen and 3 electrons from R shared via covalent bonds. The shape observed with this type of molecule, as we can kind of see, is a pyramid, and this is called trigonal pyramidal. So, there we have the basic building block species for carbon, oxygen, and nitrogen. What else is there? Next, we will look at cations, starting with carbocations, cations of carbon. Here is our standard tetrahedral carbon. What do we have to do to it to convert it into a carbocation? Well, we lose 1 electron associated with R, and we also lose 1 electron associated with the carbon, and thus we achieve our carbocation. Carbon has 4 valence electrons. There are 3 electrons associated with this carbon, as 6 divided by 2 equals 3 electrons from covalent bonds, and no lone pair electrons. What's the charge? 4 minus 3 gives us a charge of plus 1. The total number of electrons in the outer shell, including electrons associated with carbon and electrons shared with R through covalent bonds, is 6 electrons. It is hypovalent. That's to say, an even number of electrons less than 8 in the outer shell. We indicate the positive charge to be isolated in a p orbital described as an empty orbital. On first glance, this might seem rather odd. All unoccupied orbitals could be described as being positive. But the carbon here has sp2 character. A concept, however flawed, is synonymous with explaining the shape of certain molecules. The shape here is trigonal planar. The sp2 center has 3 sp2 orbitals and 1 p orbital. Think of alkenes. But in this case, there are no electrons in a p orbital, and thus we invoke the empty p orbital. When electrons approach the carbocation to form a bond, they come from either directly above or directly below, with equal probability of either outcome. The orbital containing the electrons is approaching from a direction associated with interacting with a p orbital. Thus, in light of these observations, we think about an empty positive p orbital as a useful tool. Now, normally a carbocation is trigonal planar with sp2 character, but there are exceptions where this is impossible. In this bicycle, the carbocation can't be planar, flat if you will. It is actually pyramidal, so this shape is described as having sp3 center. And now an sp3 center has 4 sp3 orbitals. 3 here are used in forming covalent bonds, so the fourth must contain the positive charge. Another scenario is where the carbocation has a double and a single bond to other atoms. The positive charge is described as being in an empty p orbital. The carbocation has sp character. This is less stable than the sp2 character carbocation and provides a linear or diagonal, if you like, shape found with sp centers such as alkynes. Now, again, there are exceptions to this generalization. This is where it is impossible for the carbocation to be linear, such as this phenyl carbocation. Because of the ring, it's not linear, but bent, with the shape analogous to an sp2 center, with the sp2 character of this carbocation made up of 3 sp2 and 1 p orbitals. When considering the p orbital is already having electrons that are utilized in forming a pi cloud, and 2 of the sp2 orbitals are used to make other covalent bonds, the positive charge will be found in an empty sp2 orbital. Continuing our evaluation of cations, we shall next look at oxonium ions, oxygen cations. To create our oxonium ion from the common neutral oxygen, we gain 1 electron associated with an R group and thus form a new covalent bond, and also lose 1 electron associated with oxygen found in a lone pair. As ever, oxygen still has 6 valence electrons. 5 electrons here are associated with oxygen, with 6 divided by 2 equals 3 in covalent bonds and 2 in lone pairs. So 6 minus 5 gives us the charge that is plus 1. In total, there are 5 electrons associated with oxygen and 3 electrons from R groups shared with oxygen through covalent bonds, for a grand total of 8 electrons, a filled octet. This is very different from the carbocation that is hypovalent and has only a total of 6 electrons. The oxonium ion can have 3 single bonds attached to the oxygen to give a trigonal pyramidal structure, or a double bond and a single bond attached to the oxygen to provide a bent structure. What about nitrogen? Here, the cation is called an ammonium ion. To transform from the common neutral trigonal pyramidal nitrogen species, we have to gain one electron associated with an R group by creating a new covalent bond and lose one electron associated with nitrogen in a lone pair. Nitrogen has 5 valence electrons, with 4 electrons associated here with nitrogen due to 8 divided by 2 equals 4 electrons from covalent bonds and no electrons from lone pairs. 5 minus 4 equals plus 1, telling us the charge. In total, we have 4 electrons associated with nitrogen and 4 electrons associated with the R group and shared with nitrogen through covalent bonds. What shape can nitrogen adopt? Well, where there are 4 single bonds to nitrogen, we observe a tetrahedral form. And where there is a double bond and 2 single bonds attached to nitrogen, there is a trigonal planar structure. On to anions. In the context of carbon, the anion is called a carbanion. From the neutral tetrahedral form of carbon, we must lose one electron associated with an R group, breaking a covalent bond, and gain one electron associated with carbon to give the carbanion. Carbon has 4 valence electrons, but here 5 electrons are associated with carbon. 6 divided by 2 equals 3 electrons from covalent bonds with R groups and 2 electrons in lone pairs. Thus, the charge is calculated by 4 minus 5 equals minus 1. In total, there are 8 electrons in the outer shell of carbon for a filled octet. 5, as we said, are associated with carbon, whilst 3 are shared with carbon from the R group. Where the carbon center is sp3 in nature, as shown here, the structure is trigonal pyramidal, as the lone pair orbital is sp3 in nature. This is less stable than where the carbon center is sp2, not depicted here, and now the lone pair is in an sp2 orbital. And ultimately, the most stable form of a carbanion, again not shown here, is where the carbon center is sp in nature and the lone pair of the carbanion is in an sp orbital. Please note that unlike the carbocation, at no time in any carbanion is the negative charge located in a p orbital. In the case of an oxygen anion, known as an alkoxide, to get here from common neutral form, we need to lose one electron associated with an R group and gain one electron associated with oxygen. Nothing has changed in the universe since we last looked at oxygen. It still has 6 valence electrons, but the number of electrons associated with this oxygen is 7, with 2 divided by 2 equaling one of those coming from covalent bonds with R groups, and 6 electrons from lone pairs. Thus, we can discern the charge to be 6 minus 7 equals minus 1. There are a total of 8 electrons, a filled octet, for the oxygen, with 7 associated with the oxygen and 1 electron with the R group. In the nitrogen series, the anion is described as an amide anion. From the common neutral trigonal pyramidal nitrogen, we must lose one electron associated with an R group and gain one electron associated with the nitrogen. There are 5 valence electrons for the nitrogen, and here with this nitrogen there are 6 electrons associated with it, due to 4 divided by 2 equals 2 electrons coming from covalent bonds and 4 electrons from lone pairs. So the charge is 5 minus 6 equals -1. There is a total of 8 electrons in this filled outer shell. 6, as we said, associated with nitrogen, and 2 electrons shared with R groups through covalent bonds. This anion takes on a bent shape.